Hello everyone, and welcome to this talk about the submodular Santa Claus problem in the restricted assignment case. So this is a joint work with Paritosh Garg and Lars Rohwedder, everyone at EPFL in Switzerland. So let's recall what is the Santa Claus problem in the linear case. So this is a classic resource allocation problem in which you have a set of resources R and a set of players P, and each resource J has some value Ej. And you can assign the resources to players according to assignment restrictions that are given by some bipartite graph between players and resources. So for instance, the second resource on the left can only be assigned to the first and second player. And we want to assign the resources to player in order to maximize the happiness of the least happy player. So the happiness of a player is simply the sum of values of resources that he gets. And we want to maximize the happiness of the least happy players, maximize the minimum. And it's called the Santa Claus problem because you can imagine that resources are gifts that you have to distribute among the players that are kids. And you want to make the least happy kid as happy as possible. So here an example of allocation. I give the first gift to the first player, the second gift to the first player, the third gift to the second player, and the last two gifts to the last player. And you see that the minimum value among all the players is achieved by the third player. He gets a total value of only 5. So the value of this allocation is 5. The Santa Claus, again, is only as happy as the least happy kid. So that's Santa Claus in the linear case, because the happiness is the sum of values of gifts. So it's a very natural problem in resource allocation and scheduling in general. And it's also the dual problem of a famous make-spend minimization problem in which you have jobs that you want to assign to machines, and you want to minimize the load on the most loading machine. So you want to minimize the maximum. And Santa Claus is basically the opposite of that. We want to maximize the minimum. So that's why it's, in a way, the dual problem of this is a very famous scheduling problem. So now let's go to the submodular case. So if I rephrase the linear Santa Claus, I am given a linear function that gives to any subset of resources some value, and we want to find an assignment respecting the assignment restrictions such that the happiness of the least happy player is maximized. And very natural extension, very natural question, what happens when f is not linear but submodular? So submodular is a more general case of linear. It's a, generalization of linear functions. And that's what we call the submodular Santa Claus problem with the assignment restrictions again. So why we study submodular functions? First, because it has a very natural property in economics that is called the diminishing returns property. And so formally, it is for any subset, two subsets of resources with X subset of Y, and every resource that is not in Y, the marginal gain, if I give you the resource J, decreases, is smaller with respect to Y than it is with respect to X. So the marginal value of a resource decreases with what you already have. So it's a very natural property. So a very simple example, imagine you're alone without food in the desert. If I give you 1 banana to eat, you'll be very happy because otherwise you will have problems. Maybe if I give you 10 bananas, you'll be 10 times as happy because, well, it's not an incredible number. But now if I give you 1 million bananas, I wouldn't say you would be 1 million times as happy because you would prefer probably much, much less bananas and maybe more water. And well, how are you going to carry this anyway? And in the Santa Claus problem, it's the same. If you give the same gifts, very similar gifts to the same kids many times, probably you won't be very happy. You would prefer to have two things very different than to have 10 times gifts that are very similar. So that's also, again, a very nice example of diminishing returns. And interestingly, from a theory point of view, some problems become more difficult with submodular functions, but also more interesting. For instance, maximizing global welfare, which is simply the sum of happiness. It's trivial in the linear case, but it's not trivial at all in the submodular case. So let's go back to Santa Claus. In the linear case, it's a very well-studied problem that was first introduced by Bamas and Svidenko in Stock 2006. And they gave a log m by triple log m approximation, where m is the number of players. And then over the years, there's been numerous improvements on the technique or the running time. And the current best approximation stands at 4 plus epsilon approximation in polynomial time. And in the submodular case, we have a more general result by Kumans et al. In Soda 2009 that implies a square root 10 approximation roughly in polynomial time, where n is the number of resources. So it's a more general result that applies to more general settings than the restricted assignment case, but that's the only thing that we know even for the restricted assignment case. So right now the state of the art stands at square root 10. And our results will be that I will show to you today is that there exists a log n approximation algorithm running in polynomial time for the submodular Santa Claus in the restricted assignment case. So let me recall first the techniques used by Bamas and Svidenko in 2006. So they introduced a linear program that is called the configuration linear program. The idea is the following. Imagine you have a guess of the optimum value to be t. Then we call a configuration C with respect to player I and value t to be a subset of resources that player I values to at least t. So in the linear case, it's simply a subset of resources that have total value at least t, and that can be assigned to player I. And then we will have one variable for each player and resource that describes how much the resources in this configuration are fractionally assigned to player I. And we have two very natural constraints from there, that each player should get in-not values, so the sum over fractional assignments of configuration should be at least 1 for each player, and that no resource should be assigned more than once, so that the sum over configuration that contains the specific resource, the sum of these fractional assignments should be at most 1. So as you can see, this linear program has one drawback is there's exponentially many variables. But it's still not a problem for Bamas and Svidenko. They showed that it can be solved with factor 1 plus epsilon in polynomial time because we can find separation record on the pure. And then from there, we have two rounding techniques against the configuration LP in the linear case. Bamas and Svidenko, they used Rohwedder. And there was another very successful technique introduced by Asapur and Fake and Savory in 2008, which is based on some local search. And both of them are based on finding a matching in some hypergraph. So let's recall a bit more in detail the approach of Bamas and Svidenko. First, we compute X star a feasible solution to the configuration LP with objective T star. Then we pre-process the solution X star to reduce to some problem in which we have log n candidate configurations per player with unit size resources. So, yeah, sorry, we have only log n candidate configurations, that's an important thing. And unit size resources means that inside each configuration, the value of resources is the same. And then we find a good choice of configurations using Rohwedder. Now we need a bit more formalism to describe the hypergraph problem. We have a hypergraph is said to be bipartite if for all hyperedges C, so we write it C because these hyperedges correspond to the candidate configuration of the previous slide. These hyperedges contain exactly one player, so it looks like this. So the players on the top and the resources on the bottom, and in a way we want to select one configuration for each player. And then you would get essentially the resources inside this configuration. So what Bamas and Svidenko get during their reduction to this problem is they arrive at some regular and uniform bipartite hypergraph. And we want to find for each vertex I in P, so each player, we want to find one hyperedge Ci such that each player is assigned a good fraction of the resources in Ci, and no resources taken more than log n times. So the hypergraph is regular. It means that Each player is contained in exactly log n hyperedges, so in red on the picture, and each resource is contained in at most log n configuration, at most log n hyperedges, so in blue on the picture. And uniform means that the size of hyperedge is the same for all hyperedges. They all have the same size k. That's what we get from the unit size resources. And we want exactly this. Find a configuration for each player, assign a good fraction of the resources inside this configuration to the corresponding player, and no resource should be taken more than log n times. And you have the assumption that the hypergraph is regular and uniform. And what's their solution? The solution is two steps. First, we sample down the resource set R to obtain a set R prime, and we keep each resource is kept with probability log n by k. So it looks like this, the resources in orange, they are selected at random and becomes R prime. So now the effect that it has is that each hyperedge has a much smaller size. Before they had size k, now with high probability they have size roughly log n. And then we sample one hyperedge for each player using low-hash local RAM. So why does it work? So the sampling, now we have a hypergraph where the degree is log n, but also the size of hyperedges is log n. And the sampling is the following. Each player selects one of his log n configuration uniformly at random, independently of other players. Then the bad event bj is simply resource j is taken more than log n times. More than log n configurations that are selected contain this resource. So what's the probability of one bad event to happen? Well, because the degree of each resource is at most log n, and because each hyperedge is chosen with probability 1 by log n, because the players they have log n configurations, it means that in expectation, each resource is taken at most once. So the probability that it's taken more than log n times, it's roughly 1 by polylog n. Second, each bad event bj depends on at most polylog n or the bad event bj prime. And why is that? I'm not going to show it formally, but if you look at this hypergraph at the top, all the parameters of interest, so the degree of resources, the degree of players, the size of hyperedges, they are log n. So it's kind of convincing that the dependencies should be polylog n. And with these two facts together, you can apply low-hash local lemma to select one hyperedge for each player such that no bad event happens. And then there's one last step. So now we have a good solution with respect to this resource set R prime, which is the smaller resource set. And now one crucial step is also that we can show that there's a good solution after sampling down, if and only if there's a good solution before sampling down. So in a way, it means that R prime is representative enough of R, the resource, the bigger resource set. And why is that? Because the expected size of each hyperedge is still log n. So you still have enough information in the smaller resource set to recover a good solution to the bigger resource set. So you apply this last step to recover a solution to the bigger resource set, and you obtain a log n approximate solution to Santa Claus. And that's the result of Bansalon Silicon. Very briefly summarized. So now let's go to the submodular case. So again, we have the same configuration in the program. We can solve it in polynomial time within constant factor. In the case where f is submodular, so only constant and not 1 plus epsilon, because the separation oracle, we can only solve it approximately when f is submodular. But it still doesn't hurt the approximation ratio, we only use constants. By submodularity, we can pre-process the solution X in a similar way as Bansalon input to arrive at some hypergraph problem. But the hypergraph problem is different. The hypergraph is still regular, so the degree of each player is still log n, the degree of each resource is still at most log n. But now, crucially, it's not uniform. That is, all the hyperedges, they don't have necessarily the same size. So you see on the left, the one is much smaller than the green hyperedge on the right. And we still want for each vertex I, find one hyperedge, Ci, such that each player is assigned a good fraction of resources in Ci, and no resources taken more than log n times. This is our hypergraph matching problem. So now the non-uniformity of the hyperedges, so the fact that the hyperedges can have very different sizes, introduces significant problems in the approach of Bensel and Srividenko. And why is that? Is because the approach of Bensel and Srividenko has this first step of sampling down the resources that is crucial to apply Lovász-Lokó lemma. And they need that roughly the size of hyperedges in the sampled down resource set is roughly log n, to maintain first low dependencies, and also that the fact that the smaller resource set is representative enough of the bigger ones. And in our case, it's impossible to obtain such a property with just one sampling down, because the hyperedges have very different sizes. So if we sample down too aggressively, so we keep each resource with very small probability, then the resource sets might not be representative of R anymore. It might be impossible to recover a good solution from the small resource set to the bigger one. And if we're not aggressive enough, so we keep the resources with a relatively high probability, then the hyperedges that are very big, like square root n size, so size of square root n, can still have a size polynomial in n. So we don't have polylog n size, and it's impossible to argue about the dependencies to be polylog n because it's not true. So our solution, general big picture of our solution, is first that we want to select hyperedges for each player, such that any hyperedge C will intersect the selected hyperedges C prime that are smaller than C, not too many times. And if we have such a property, then we can do some iterative procedure from the bigger hyperedges to the smaller ones. And when small hyperedges arrive, we already have a solution on the bigger hyperedges. We allow the small hyperedges to steal from the big ones. And if we have the first property that each hyperedge is never intersected too many times by smaller hyperedges, then it will show that no hyperedges loses too many items. So, a bit more formally, we first do some geometric grouping of the hyperedges according to the size. So, for any hyperedge that has size between log to the power k minus 1 to log to k of n, we put it in the kth group. And then we also build a hierarchy of resources, Ri, where Ri plus 1 is obtained from Ri by sampling down with probability 1 by log n. So we have a nested sequence of resource sets, and each resource set corresponds in a way to one group of hyperedges. So there's, for each group of hyperedges, there's a set of convenient granularities such that these hyperedges have size roughly polylog n on this resource set. And then we use Lovász-Lokó lemma to sample one hyperedge for each player, such that for any hyperedge in the hypergraph, if I look at the sum of intersections with this hyperedge with smaller hyperedges that were selected, it's not too big. So that's, in spirit, still the same thing as Bensel and Srividenko, but we have one crucial twist, is that we look at this intersection restricted to the resource set of convenient granularity. And this is a very crucial step to obtain our solution. And then, why does this work? First, with high probability, if I look at the smaller hyperedges that might intersect C, but restricted on the resource set of convenient granularity, I have an expectation size polylog n. So with high probability, I can argue that the size is polylog n. And now it recovers the low dependencies property of Bensel and Srividenko. That is, roughly, if I look at the size of hyperedges, it's polylog n. So there's a hope to apply Lovász-Lokó lemma, because in expectation, the probability of each bad event is still 1 by polylog n. And second, the intersection with other configurations, it's still big enough, so polylog n, to be representative enough of the intersection with the whole on the, when I don't restrict to the resource set, the smaller resource set. So it means that I can do this iterative procedure. I first start from the big configurations. I have a solution on the very small resource set. Then I augment the solution to the slightly bigger resource set, still on the big hyperedges, and I add the small hyperedges, allowing them to steal from the big ones. And I iterate this over all the resource sets from log n to 1. And we get a good solution in the end, the whole resource set. So we get a log n approximate solution. So to wrap it up, we have first, we did in a way a similar reduction as Bamas, but crucially, submodularity was captured by the non-uniformity of our hypergraph problem, and it really introduces some difficulties that were not here in the first paper of Bamas. So the general result is we obtain a log n approximate solution where n is the number of resources. But there's still very interesting open question. First, getting a constant factor approximation would be very interesting. It's an interesting open problem. It should be possible given the results that are known in linear case. So if I recall in the linear case, the best known is 4 plus epsilon approximation in polynomial time. And also from a technical point of view, here we show that we can use the local lemma technique to obtain a good approximation. But I said in the beginning that there were two main rounding techniques against the configuration linear program that were very successful in the past, and the second one is some local search. And in our case, when the function is submodular, it's really not clear how to adapt this technique in the submodular case. So that would be very interesting, especially since the best approximation ratio that are 4 plus epsilon currently, they are obtained not with Lovash local lemma, but with local search. Lovash local lemma, I think the best result is only some big unspecified constant. And of course, what about more general valuation functions? So here we have one submodular function and assignment restrictions, which is already a more general problem in the linear Santa Claus, but there also, you could imagine that each player has one arbitrary submodular function to himself that is private. And in this case, the only thing that's known is the result of Gummans et al. In 2009 that gives square root n approximation. And it's probably a very interesting question, probably very challenging to improve that, but a very interesting open question. So that's the end of my talk. I'd like to thank you for your attention, and I hope to meet you in live sessions.